And we're back. Welcome back and happy Tuesday. Today we will pivot to discussion on virtual memory. Now, virtual memory is a top 5, top 10 concept in operating systems, and modern operating systems use virtual memory with the exception of mobile device operating systems, which for reasons of their small footprint cannot afford the extra overhead of mechanisms for virtual memory. Before we begin, we'll get to some administrative bits. The reading is new reading up by the 19th of November. Please make sure you're keeping up with the reading. Operating system concepts, section 10.1 through 10.6.4, that's pages 389 to 425. As of today, there are 7 class meetings left. Written exam number 2 will be Tuesday, the 17th, next week, in 1 week, out at 9:30 in the morning. It will be a 30-hour exam. The details, I'll go over all of the questions on the class meeting, as well as answer any questions that you might have. The last day of classes will be Thursday, the 3rd of December. Reading day will be the day thereafter, the 4th of December. I believe we will have Division Day, so please look out for those announcements from the division chair. Residence halls will close on the 25th of November. That's the day before Thanksgiving at 5 p.m. And those who are on campus physically will be heading home to return in the spring semester. The scheduled final exam period for this class will be Thursday, the 10th of December. That should be 2020 at 10:30 a.m. to 12:30 p.m., during which we will do project presentations. Again, that should say December 10th, 2020. Finals will be ending on the 11th of December at 8 p.m. And on that date and time, you will be handing in your final projects. We will have a final project for this class. So you'll be presenting on your final project on the 10th, and on the 11th, you'll be handing in all of that work, the slides, the code, as well as the write-up. Okay, so why don't we begin? So the objectives of Chapter 10, Virtual Memory, are threefold, at least what we'll be covering. We won't be looking at the relationship between shared memory and memory map files, and we won't be looking at how kernel memory is explored, not this year's cohort, but we'll be looking at how you describe the benefits of a virtual memory system, and look at the concepts of demand paging and page replacement algorithms, and the allocation of pages to page frames, and we'll discuss the principle of the working set model. Okay, so let's take a look at some background. Now, code certainly, as we've been talking about it, it needs to be in memory in order to execute. But it's very rare that you use the entirety of your program throughout the course of its execution. Let's consider code for error processing when you have exceptional conditions. You might decide to write down a journal log entry or send a message out somewhere. Or perhaps there are some unusual routines that you don't use very much, or perhaps there are some very large data structures. In this case, with very large data structures, that's particularly interesting because maybe you have a whole database, but you're only using that portion of the database in your program corresponding, for example, to students in my class. And so the entire program code is not all needed at the same time. And so if you're able to execute partially loaded programs, this helps you immensely, and this is the subject that virtual memory enterprises to solve. And so if you're able to execute part of your program or partially loaded programs, that means your program's not constrained by the limits of physical memory. Now, certainly when we talked before, we said here is your program, and your program, its addresses in the instruction stream, 1 through n, is divided up into logical chunks, and we call these pages. And these pages are then loaded onto similarly sized chunks called page frames in main memory. And so that means when you're executing in your program, as we have discussed before when we talked about main memory, is that your program is constrained by the limits of physical memory. Once you run out of enough physical memory to store the pages for your program can no longer execute. And So what this idea of partially loaded program execution means is that each program can take up less memory when running. And if each program only takes up enough memory needed for that portion that's currently executing or being used, well, that means you can use the rest of memory for other programs to run or execute their partial amounts of their logical address space. And so in doing so, this partially loaded program execution allows each program to take up less memory when running, which stands to increase CPU utilization because now you can have more processes running at the same time, maximizing use of the CPU. And you can do so with no impact to increasing in response time or turnaround time, as we saw before when we talked about scheduling. Because you're also loading parts of programs in and out of memory, that means you're loading and unloading less sized chunks of program in and out of memory, which lowers the burden of swapping because you're not swapping as much memory. And that means that each user program is therefore also going to run much faster. And so virtual memory is a win-win on all cases. And so virtual memory strives to separate the logical memory, how you look at the logical set of offsets or addresses in your instruction stream for your process. It separates it from physical memory, namely the set of addresses for your main memory. And so the big breakthrough with VM, virtual memory, is that only part of the program needs to be in memory for execution, and it's that part that you're currently referring to. Now, referring to is an interesting thing. It can mean many things, and that primarily means both the memory that you access, that's the variables and the data structures, as well as the instructions that you reference in order to decode instruction and set up computations. And so only part of the program needs to be in memory for execution. And so the logical address space, therefore, can be much larger than the physical address space. So here's your process. And let's assume your process address space was very big, and you could have instructions labeled 1 through n, for n is some really large number. You can also have your main memory much smaller than the logical set of addresses for your logical set of instruction streams for your process. And in that case, if you only need a small chunk at a time where you're currently executing, both for reference of instructions as well as variables and data structures, well, you only need to have that particular small localized region, that page, load into memory. And so relative size-wise, you can have a process that logically has a much larger address space than the available physical memory. And so this allows, in addition, address spaces to be shared by several processes. And so you ask yourself, well, why would you do that? Well, certain blocks of code, like your system libraries, when we talked about linking, some of those instructions might be system libraries that your program uses. And if these system libraries are only read by your process, well, other processes that need to use them, why have separate copies? Have the same copy of your system library, is my system library, that other processes attach to their local address space. So here's a second process, and here's that same system library that it attaches to its logical address space, but it's really the same physical page in memory that's just shared by multiple processes. And so this allows for more efficient runtime images. They're smaller, and if it's read-only, well, you can just pin it in memory and allow all the processes to share it. And so then it's just the mapping of this physical address space into the logical region for your process. And this allows for more efficient process creation as well, this virtual memory, by tinkering with the relationship between the parent process and the child process. And we'll talk about that in more detail. And this also means that you can have more programs running concurrently because you're only looking at mapping small regions or pages from a process within main memory. You can have many more processes because each one then uses less memory in order to execute its instruction. And then this also, and we'll talk about this part later, you need less burden on I/O in order to load or swap processes between your backing store and your main memory. And we'll talk about that in a little bit. And so the virtual address space is a logical view of how the process is stored in memory. And so you start at some initial address, and this is that instruction stream we talked about. So here's your process, and you start at some initial address offset, and maybe address 0, and you have contiguous addresses up through some number n or n minus 1, and that represents the appearance of contiguous set of instructions, and we've been calling that our instruction stream. Now they're numbered, and the set of offsets referring to the instructions in instruction streams is called the logical address space, the logical. And so the physical memory organization, we said before, is located, main memory, into frames. And these frames are consistent chunks of physical memory, and these chunks are the same size as those chunks, the pages, for your logical address space. And so we also discussed the memory management unit, or the memory device, the MMU, and its responsibility is to map from logical offsets in the process to physical addresses in main memory. And so this virtual memory can take form as demand segmentation. We're talking about memory segments, but the focus we're going to talk about on, or focus on for this module, is on demand paging. And so what this demand part means is that as you refer to some address, whether it's the fetch of an instruction or the reference to some variable or some symbol for variable or data structure, you're going to bring in that page into memory from the swap space or from disk. All right. So in this figure, this schematic is in the book. We have on the left-hand extreme, we have our process, and this is our logical address space. And this logical address space has a number of chunks of logical address, and we have our instruction stream going from address 0 to some maximum address n in our virtual memory. And so here we have our pages for the process, page 0, page 1, page 2, and so forth. And these pages are also the same size as your main memory. And here is your physical memory. And our physical memory is organized into those same chunks, and these are our page frames or frames. Now, of course, we have a memory map that translates from a logical address that's generated by the CPU into a frame. And we said this page table is responsible for doing that, and the mapping is performed by the memory management unit, or the MMU. And so this memory map we call the page table. So in similar fashion, for virtual memory, we're going to use this memory map. Now, the thing that we also talked about was the backing store. And the backing store was a fast region of disk, and the in-memory form of a process page is stored in this backing store. And so when we ran out of free frames in which to store the page of a process, we would then evict or kick out a process's page from a frame and send it by writing it to the disk, to the backing store. And then likewise, we can bring in a page onto a page frame from the backing store. And so the free frame list was the mechanism that we used in order to do that. All right. And so the virtual address space is usually designed logically from stack to start. And we typically have the stack starting at the maximum address. That would be from instruction or offset, whatever that n is, some maximum. And the stack grows downward towards 0. And so we said before, the stack is automatic storage, and it's used for parameters, for local variables, for return addresses. And so this stack is going to grow when we add parameters to call a function, and it's going to shrink when we return from the function and release those parameters we no longer need. And so the stack grows downward, and then the heap corresponds to all of those dynamically allocated structures. It could be new in Java. It could be malloc in C, and we're going to stick to the C definition because that's the examples that we've been given. So the heap grows upward from the smaller offset towards the larger offset, and the stack grows downward from the maximum offset down towards the first offset. And so this leaves other regions. We have a code section, and this code section was the instructions of your program. We have the data section. This data section was your static allocation and global variables, and then heap grows upwards from the next segment from that. Now this leaves a huge hole in the middle of your address space. And so as you will note, we have some usage from the stack and it grows and shrinks. Usage from the heap, it grows and shrinks. As you malloc, it grows. As you free, it shrinks. And then this hole is relatively large. And so we often call this logical or this virtual address space, we call it sparse. It's sparse because the majority of it is a hole. And so when we arrange them this way, we maximize address space usage because we have this part at the top that grows and shrinks, this part at the bottom that's filled with code and data, and the heap grows and shrinks up, leaving the majority of our virtual address space open and free. And so there's a large amount of unused address space in between the two, and this is a hole. And when you do this, this sparsity benefits you for virtualization of your memory. What it means is that the vast majority of the memory needed by this process is unused. And if it's unused, you don't need to have the pages associated with chunks for this whole. You don't need to have them all loaded into memory. And so this helps you in managing or minimizing the amount of memory needed by your individual processes. And so that means that there's no physical memory that's needed until the heap grows or the stack grows, because the stack begins as empty until you start allocating local variables, calling functions, and so forth. And likewise, the heap grows as you start doing mallocs to allocate user-defined types and variables and primitive types in your program. So in the beginning, this heap is 0. It is also part of the whole. In the beginning, the stack is also 0. It is also part of the whole. And so in doing this, the sparse representation for the layout of your program's runtime image benefits virtual memory because it minimizes the number of pages you need, and it only allocates pages as your program executes, as it grows in its space usage. And so the sparse address space gives you holes left for growth, and you can do all sorts of stuff, fill it with stack and heap information, also dynamically linked libraries as well. As you use system calls, the stub loads this dynamically load library, and that occupies your DLL if it's Windows, or your shared object if it's Unix. It occupies segments or frames within this hole. And so you can also do shared memory. When we did a shared memory create, that shared memory was also another entity that occupies frames associated with this whole. And so certainly these shared memories, you can also use them to minimize the image requirements for your process because you're sharing data or pages between two processes. And so the shared memory, by mapping pages read-write into a virtual address space, each one of the processes then takes these frames that are shared and maps them into their virtual address space. Pages can also be shared when you do a fork to create a child process. The parent and the child can actually share pages associated with the code of that process, and in some cases with the data as well. And this can immensely speed up process creation because you're not creating an entire new copy of the process. You're only creating parts of it, small pages, localities that comprise where they're different from one another, the parent and the child. And so this is an example of a shared library using virtual memory. And so here we have two processes, process P1, you'd imagine on the left, and process P2 on the right. And so here we have the stack and the heap, stack growing down, heap growing up, and then we load a shared library. We have shared pages here mapped into the virtual address space of process P1, the virtual address space of process P2. But if we were to draw main memory here in the center, well, we have the frames associated with the shared pages that are pinned in main memory, but they're just mapped into the logical virtual address space of the two processes, P1 and P2. So let's take a look at demand paging. And so one of the things we could do is bring the entire process into memory when you load that program. Now, of course, you could also bring a page into memory only when it's needed. And so here we have two programs, program A and program B. We have all of the frames assigned for the pages for program A, and then we have frames for program B. And now if you look here, we have our backing store. This is our backing store. Sometimes it's called swap space. Swap space. There's backing store. And we have here only 4 pages for program A are in main memory. So we have 4 frames from main memory assigned to program A. And we only have 3 frames of main memory assigned to the 3 pages for program B. Now, if we look at all of the pages on the backing store, well, we see many more pages than there are physically loaded for program A and B in memory. And so if you only bring a page into memory when it is needed, that reduces the amount of I/O that's needed. And so that I/O, again, is the swapping out when you're writing pages for one program into the backing store, and when you're reading pages into memory from the backing store. So because you're minimizing or reducing the number of pages that are written and read to and from the backing store, you're minimizing the amount of I/O that's needed, and that also tends to make your process response time much, much faster, as well as use less memory, because that I/O is going to incur an order of magnitude slowdown, both for the disk device for backing store to operate, as well as to send these pages across the system bus to get to main memory using a DMA transfer. All right. And so similar to a paging system with swapping, and this diagram is from the book, we're going to reference a page. And when you reference a page in a program, remember that's a logical construct. Either you can have an invalid reference for an instruction. So let's say that's instruction 1, 2, up to including instruction N. And here we have instruction 1 up through instruction, say, K in our program B. And so let's say program A references instruction 2. One of 2 things can happen. Either it's an invalid reference, meaning that it's trying to refer to some piece of memory that is off limits or outside the bounds of the block of instructions associated with program A, or it tries to access that instruction or that instruction in its instruction stream, and it refers to a page that's physically not in memory. Now, if it's not in memory, what do? You say, okay, well, I'm going to locate it on the backing store, and I'm going to load it into a frame from the free frame list in main memory. And so this demand paging is this idea of the lazy, meaning like it waits until it needs it, the lazy loading of pages from the backing store into an allocated frame from the free frame list in memory. And so a lazy swapper never swaps a page into memory unless the page will be needed. And so a swapping feature or swapper process in an operating system that deals with pages is sometimes in the literature therefore called a pager. It swaps in and out pages lazily when you get a reference to a page or an instruction in a page that is not currently loaded or allocated to a frame in memory. Okay, so with swapping, what happens? A pager has to determine which pages will be used before swapping out again. And so this idea of references is really, really important, because as you access memory locations or maybe you're indexing into a large array, you need to know, okay, well, what page is it going to refer to? And so instead, the pager only brings in those pages into memory that it knows are going to be referred to. And so the natural question for this is, how does this all happen? How does the pager determine what set of pages it needs to bring into memory? Now, this could be an educated guess, or it could be discrete as it needs it. So now you need new functionality with the memory management unit in order to implement this idea of demand paging. It needs to know whether or not, or track whether or not a page is physically in memory or not. And so if pages that are needed are already memory resident, then okay, it's no difference from this on-demand paging. If a page is needed but not memory resident, then you need to detect it. And once you detect it, then you load the page into memory from storage, and you have to be able to do that, and this is the key part, without changing the program behavior. So that means you're going to have to know what that instruction was that generated that reference to some page instruction that was not loaded into memory, and then you need to replay that instruction as if nothing happened. So this has to happen also without the programmer changing the code. It has to happen between the operating system and the CPU as it executes instructions in your program. And so with the page table, there's a modification that the pager has for this virtual memory, and it adds a valid invalid bit. And so we have a column, an entry in the page table, like we talked about before, and we're going to have the frame number, and the index 0, 1, 2, 3 into the page table refers to the page number. And so that hasn't changed, but what has changed is we associate a valid invalid bit with each entry in the frame table, in the page table. And so this valid invalid bit can be set to V for valid. That means that the page associated with that frame identified is now loaded into that frame and in memory. Now, what the I value is for this valid invalid, it means it's invalid. And this can mean one of two things. It means it's not in memory from the perspective of the paging system and its interaction and role in virtual memory, but it's also used to check if that address in the program, in its virtual addressing system, its virtual address space, if it's a valid address that respects the bounds of what the addresses are that belong to that particular process. And so the main modification to the page table is this entry where each frame entry is associated with a valid or invalid. And it's used to identify whether or not that particular page is resident and loaded in the frame in memory. Okay, so this is what happens to the page table when some pages are not in main memory. So in this figure, and this figure is in the book, we have the backing store on the right. We have physical memory next to it. We have the page table augmented with the valid invalid bit. And then we have our process, our logical address space, our virtual addressing. And so here for the process, we have our pages. We have page 0 through page 7 for a total of 8 pages. And then we identify just the code block associated with each one of the pages in the virtual address space for a process. And so here we have page 0 is loaded in frame 4, and it's valid. It's valid because it's physically loaded into a page frame number 4 in main memory. Then we also have page 1. It is not loaded, and we'll notice here the entry for page 1 in our page table, it has an I, meaning it's invalid. But we do have that the contents of page 1, which is B, is loaded. It's in the backing store. And so we also have page 2 for a program. Contents is C. It's loaded in frame 6. So if we go to frame 6, it's loaded in. So we have valid. And then lastly, page 5 has contents F. It's loaded in frame 9. So if we go to frame 9, it's loaded, so it has valid, and everything else is invalid. But you do notice we have page 0, we have page 2, we have page 5. They're all valid and loaded in main memory. Now, the other pages, page 1, 3, 4, and 7, and 6 and 7, you notice they're all loaded A, B, C, D, E, F, G, H. All of the pages are loaded in the backing store. Only some of them are valid because some of them have been loaded or assigned, allocated to frames in memory, and they're resident in memory. And so now what would happen is if an address, say some piece of code here in page 0, referred to something, say in page 3, it would say, okay, page 3, it's invalid. And then the system would wake up and trigger a page fault, which is an interrupt to the operating system, a trap, and it would go through the action of loading from the backing store that particular page and assigning it to a free frame from the free frame list and marking that entry then as valid and filling in the frame in the correct page table entry. And so if there is a reference to a page, the first reference to that page will trap to the operating system, and this is called a page fault. And so this page fault, the operating system service routine, looks at another table to decide, A, is it a valid reference? If it is an invalid reference, you've violated the bounds of the memory that process is allowed to access, and you abort the process. or is it just not in memory? Now, if it's not in memory, what happens? You find a free frame from the free frame list, and then you swap the page into that free frame using a scheduled disk operation. So now this is where you set up the transaction, you being the CPU, with the I/O controller for the disk device, and set up the DMA transfer, and you're waiting for the buffer for the I/O device to fill, and then you're going to transfer that buffer to that free frame associated with the free frame list for memory. And so you swap page into the frame using a scheduled disk operation, and then you reset your table, modify your page table to indicate what the page is, and that it's now in memory, and you set its valid bit. And then the last part is really important. You restart the instruction that caused the page fault. You're going to replay that instruction. So the instruction causes the page fault, and then you know where the program counter was when the page fault happens. You go back to that instruction, rewind the program counter, and replay that instruction. And then it proceeds as if nothing happened. Now, of course, when this swap of the page into the frame happens, that takes some time. And that time has the effect of slowing down the execution. But the good news is that this doesn't happen all the time because the frames are big enough that it doesn't happen on every instruction. And so this schematic, and it's in the book, it gives a relationship between all of the steps that happen when a page fault occurs to get that page loaded from the backing store into main memory and how that page table is updated. So step one, you load some reference. You're trying to access some memory or variable. You access the page table. You see that it's invalid. So then the next step, two, you trap to the operating system, and it locates the page in the backing store. It allocates from the free frame list a free frame, and then it loads that page from the backing store into that free frame. It knows what that free frame is, fills in the free frame number in the correct entry in the frame table, and then it changes that invalid to valid, and then it resets the program counter to replay that instruction. And so now the next time it accesses the page table, it sees that it has a frame and it's valid, and it executes as if nothing happened. All right. And so in the extreme case, one thing you could do is start a process that has no pages in memory. And with that, the operating system sets the instruction pointer to the first instruction of a process. And in this case, your process is effectively empty, and you're going to refer to that main entry point in your process. And none of the pages of your process are in memory. So the first thing that happens is you look for some address associated with main, and it causes the page fault. And so then starting out with this pure way of loading, even from the beginning, every single address associated with your program, including the main entry point, that's called pure demand paging. And so for every page needed, including the first page needed for your main entry point, and then subsequent page faults occur every time you access variables or data structures or code. Those pages are brought in as needed. And so for every other process, the pages are on first access, as well as the entry point, as well as all data structures and functions and instructions. So if you execute an instruction that's off the edge, say instruction K here, the next instruction K plus 1, well, if it's not in memory, it's going to trap, cause a page fault, and that next page is going to be loaded into memory for that next instruction. And so every address generated by the CPU is, if it causes a page fault, that page is brought in, and that's called pure demand paging, when you assume that there are 0 pages at the beginning for your process loaded into page frames. And so a given instruction can access multiple pages, could cause multiple page faults, because an instruction could have operands like add A to B, where A and B are in different pages in your process. Also, it can, maybe if you're iterating through an array, you're saying one position in the array is equal to another position plus another position. Well, those could cause 3 page faults, as each one of those array positions are in different physical pages for your process. And so if you consider also the fetch and decode of instruction, both the instructions and the operands, they can all cause page faults. But this is decreased because of something called locality of reference. It means that things that you access frequently tend to be close together. If you say int a equals 1, int b equals 2, and you say int c equals a plus b, well, they tend to be close by to one another, close by meaning within the same page. And so this page faulting is minimized or made smaller because of this locality of reference. Things that refer to one another tend to be close by within the same page. And so you need hardware support for this demand paging, and this is typically in the form of this valid invalid bit. You also need secondary memory, and this is your swap space, which is also your backing store. And you also need this ability to replay instructions, the instruction restarts, and that happens after that page fault is finished loading in that page into an assigned page frame from the free frame list, and this is performed by the operating system. And so this instruction restart, if you think about an instruction that accesses several different locations, like the move of a block, you're trying to take some piece of memory and move it to another address. Well, you're going to automatically increment and decrement the location, and you're going to restart the whole operation. But what happens then if you restart if the source and destination overlap? Well, there's a little bit of a problem. Well, do you restart the whole instruction? Do you restart part of the instruction, just the access? So let's take a look at the performance for the worst case of demand paging. And so you trap to the operating system, that's your page fault. You save the process state, the registers, including the program counter. You determine that the interrupt was a page fault. Okay, you do that, check in the operating system, look at the service routines, call the right one, and you check that the page reference was a legal one. Is it the issue that it's outside of the block that the process owns, or is it that the page is not in memory? And so you determine also the location of the page on the disk, on the backing store. And then you issue a read from the disk to get it to a free frame. That's after checking the free frame list and allocating a free frame to that particular page that's on the backing store. And so you issue that read request, and then you wait in a wait queue for the device until the read request is done. And then you wait for the device to spin and actually take that data, push it into its device IO buffer, and then you do the transfer of the page to the free frame, and that's through a DMA transaction to move that from the buffer for the IO device, the disk backing store, to get it into memory. And so while you're waiting for all of this to happen, you allocate the CPU to some other user because you're on the wait list for that device, for the IO device, for the disk. And then you receive an interrupt from the disk that says, okay, the IO is completed. And then what do? You save the registered and process state for the other user that got the CPU in step 6, and then you determine the interrupt was from the disk, and then you correct the page table and all the other tables to show that's where you update this valid bit be valid, that the page is now in memory. So now you wait for the CPU to be reallocated to you by the short-term scheduler, since you're now on the ready queue and not on the wait queue for the backing store disk device. And then you restore the registers and the process state and the new page table, and then you resume as if nothing happened, this instruction that was interrupted by the page fault. And so all of that happens, and the one part, that wait time, where you're doing the copying, you allocate the CPU to someone else instead of waiting the CPU, because you're now in an IO burst and no longer in a CPU burst. Okay. And so there are 3 major activities in play. You service the interrupt, you read the page, and that happens a lot of times, and you restart the process. Now let's assume that the page fault rate is some probability p between 0 and 1. If p is 0, that means there's no page fault. So p is the probability of a page fault. And so if p is equal to 1, that means every reference is a page fault. That's a catastrophe. That usually never happens, but since it's a probability, we have to talk about it. So we define something called the EAT, the effective access time, and this is 1 minus p. That's the rate for a non-page fault. So that's a non-page fault And that non-page fault, that probability 1 minus p, for those non-page faults, you can have a direct memory access. So that's relatively fast. But for the case of a page fault, you're going to have other overhead. And that's going to be the overhead of performing the page fault itself, the interrupt service routine to execute, to swap the page out for a page that is evicted, and to swap a page in, that's a page that's copied from the backing store into a frame allocated from the free frame list. And so all of that takes overhead. And this second term here for the page fault case happens at a rate of p, where p is the page fault rate, and that's going to be where your slowdown occurs. And so if you are dealing primarily with memory access, this is just a normal process execution. But if you're dealing with a page fault, you have to deal with the overhead of swapping as well as context switching to that process that's going to get the CPU while you're waiting for I/O. Okay, and so in this example, we have a memory access time of 200 nanoseconds, and that's typical. And the service for a page fault is 8 milliseconds. Now, nanosecond is much smaller than millisecond. Millisecond is 10 to the negative 3. Nanosecond is 10 to the minus 9. Microsecond is 10 to the minus 6. And so you'll see that the memory access is much, much smaller, much faster time than the page fault service. And so the effective access time, the EAT, as it were, is 1 minus p times the 200. That's in nanoseconds. Okay, and then our page fault, when that happens, that's p times 8 milliseconds. Now, 8 milliseconds is orders of magnitude bigger than the 200 nanoseconds. So that's 8 million. That's p times 8 million. That's our page fault service rate, service time. And this is our 1 minus p at the 200 nanoseconds. So we're assuming this is nanoseconds. A millisecond is a million bigger than a nanosecond. All right, so we do a little bit of arithmetic, and we get 200 plus p times just under 7.9 million nanoseconds. And so if one access, and this is dealing with probability, one access out of 1,000 causes a page fault, right? So that means we have one page fault for every 1,000 accesses. The EAT is 8.2 microseconds. And so this is a slowdown factor of 40 times relative to what we had if we were just doing pure memory access. And so essentially, you want a performance degradation that's no more than 10%. And so if we figure 200 nanoseconds of memory access, 10% of that increase would be 220, because we're adding 20. 20 nanoseconds is 10%, 200 nanoseconds. So that means this expression has to be less than 220. And in order for this expression, 200 plus just under 7.9 million nanoseconds times p, in order for that to be less than 220, do a little bit of algebra, subtract 200, subtract 200 from both sides of the inequality. We're left with 20 is greater than 7.9 and change million times p. So that means p is 0.000025 probability. So here, what we're doing is we're saying and solving for what the probability should be for the page fault rate in order to have a degradation in performance for a pure memory access that's no more than 10%. So this corresponds to this probability, one page fault in every 400,000 memory accesses. So that just says that a page fault should be relatively rare, should be a small probability. Now, of course, from a performance tuning standpoint, this would mean that you have to set your page frame size, and therefore your page is large enough that your locality of reference will pay for this 1 out of every 400,000 memory accesses. All right, and so you can demand page optimizations. You can make this a lot faster through a number of different tips, tricks, and techniques. One is to make your swap space I/O faster than your file system, even if it's on the same device. And so your swap space, therefore, is allocated in larger chunks because less management is needed than on a file system. If you have your swap space chunks larger, you get that benefit of making the transfer of blocks much less frequent and increasing your locality of reference. You could also copy the entire process image to swap space when you load the process. So the first thing that happens is when you first load your process, you first start it, you chop it up into pages, and then you put all of the pages of your process 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. You start out and you put the entire process worth of pages in your backing store or your swap space partition on your disk. And when you do this, of course, now you've already pre-digested, if you will, your process, and now it's just a matter of accessing the virtual addresses and assigning those pages from the backing store into the allocated frames from the free frame list. And this is used in older versions of BSD Unix. And so you could demand page in from program binaries on disk. You could absolutely do it directly from the program binaries instead of using the swap space, but then discard them rather than paging out when using the free frames or trying to free up frames. So some do that. So some will say, okay, well, I have my executable. Here's my swap down here, and here's my executable. I'm going to take my executable and chop that up and demand page those into free frames, but then I'm not going to swap out those free frames. I'm just going to throw them away when I need to deallocate them. And so you still need to write to swap space, but the pages are not associated with the file. Things like stack and heap, those pages aren't associated with any particular file. And so those are sometimes called anonymous memory. And these pages are modified in memory, but not yet written back to the file system. And so even with this faulting in pages directly from the program binary, that works very well and fits well for code, but it doesn't work as well for things like stack and heap because those things still need to be written back. Now, for mobile devices, they typically don't support swapping. Instead, they demand page from the file system and then only reclaim the read-only pages, such as the code. And so if you have heap and you have stack, those are not reclaimed when you need to discard a page frame from a page frame because you need a new page for a newly executing process. And so it says read-only pages can be deallocated, thrown out, but read-write pages, those are not deallocated. And so those are optimizations that they make for pages in virtual memory. And so another optimization, another thing that happens is something called CopyOn write or cow optimizations. And this relates to the relationship between a parent process and a child process. When you first fork a process, we said that the child process is a copy of the parent process. And so if the child is a copy of the parent, why not share the same pages? And so then it only once one of the parent or the child decides to modify a shared page, only at that point is that page copied. So that way, the fork, the creation of a child process, is almost for free, right? It happens very fast. You're just creating a new process control block, and then they're sharing the same physical pages, both the parent and the child. And so this is more efficient for the process creation, and this really benefits you performance-wise when you're forking a lot of child processes. And so in general, free pages are allocated from what's called a pool of zero fill-on-demand pages. And what that means is that all the pages for every process map to a single ZeroFrame. And this is in physical memory. And you don't get any memory pages until you write to that page. So the first thing you do is you try to reference an instruction. You reference an instruction, all of a sudden a page fault happens from the zero fill-on-demand frame, and then you get a new page that's allocated to you, and the OS automatically zeroes it out. And so then what this does is that it allows the kernel to make a page eviction or reclamation decision. If the kernel can't allocate more memory when you write, it has a decision to make. Either it kills your process or it kills another process in order to get more memory if it ran out of pages. And so this idea of using a single zero frame associated with every process as it starts, it allows the entire decision to be up to the kernel about how it should proceed in low resource situations. And so this memory pool should always have free frames for fast demand page execution. You never want to have this free frame list be depleted completely, you always want to see once it approaches a threshold whose pages, whose page frames you're going to reclaim, meaning you're going to throw out some pages, push them out to the backing store, or just delete them altogether and deallocate the frame and make it go back to the free frame list. And so one question that you might ask, why zero out a page in the kernel before allocating it why zero out a frame before allocating it to a page? And the answer to that is security, right? Because if code for some other process was there, especially shared libraries, you want to zero it out because you don't want someone to be able to access raw memory that was allocated to you. And so there is a variation of the fork. It's called vfork. And vfork can be very dangerous, so you should tread lightly. And this vfork system call has the parent suspend and using the child using that copy on write address space of the parent. And so this is designed to have a child call the exec, and it's very efficient, but you should be very careful when you use vfork. It's a variation of fork where the child is using the address space of the parent. And so here is an example of two processes, and they're in physical memory, and this one is the parent, process one is the child. And let's assume they're using shared pages, and these pages are associated with page frames that have been allocated to physical memory. And so we have process one, and we have process two, and all of a sudden process one, let's say it's the parent, could be the child, decides to now write to page C. This copy on write then creates a copy of page C, and now it has its own copy of that particular page, which originated from the parent when that fork call occurred. And so after process one modifies that C page, that page C, only then does it cause the copy, and now process one writes its own copy of that page. And so this speeds up tremendously the forking process when you have a parent and child process, a parent forks the child process. And so with that, that's all I had for today. As usual, please make sure you're keeping up with the reading. Please stay healthy, please stay safe, and I will see you all